Welcome to the electronicshobbyblog.com. I'm your host, Dominic Soldano, and today we're going to talk about diodes. Rectifier diodes in particular. We'll look at some practical applications in the lab, as well as learning a little bit about the theory. So come on along for the ride. Let's get started. Like resistors and capacitors, diodes come in a wide variety of types, shapes, sizes, each with special characteristics that are designed to meet a specific application or range of applications. Rectifiers, which we're going to talk about today, are just one type, but there are also Zener diodes, pin diodes, tunnel diodes, Schottky diodes. That's just too many to talk about in one video. All diodes have certain characteristics in common. For instance, every diode has an anode and a cathode. The anode is usually drawn on a schematic diagram as an arrow pointing away from the positive terminal, and the cathode is usually a vertical line drawn at the point of the anode, on the schematic that is. Actual diodes have some kind of band around the barrel of the diode indicating which end is the cathode. Here you can see it as a white stripe on the diode itself. Diodes normally only allow current to pass in one direction, from the anode to the cathode. Zener diodes, however, are designed to allow current to pass in both directions, but in the reverse direction, they limit that current flow to a specific voltage. Therefore, Zener diodes are often used in voltage regulator circuits. For our discussion today on rectifier diodes, consider that the diode only allows current to pass in the forward direction and blocks any current when it's reverse biased. Here's an IV characteristic curve for a typical diode. Notice that there's a forward junction conduction point where the diode starts to conduct. For a silicon diode, that's right around 0.7 volts. And then the voltage drop across the diode stays pretty consistent. There's a little variation, we'll see it in the lab, but for the most part, the voltage drop across the diode stays pretty consistent over a wide range of currents. When the diode is reverse biased, there's normally a little leakage current. It's normally in the microamps. There is a point, however, where the voltage gets so high that the diode breaks down and allows current to flow in the reverse direction. That voltage can be pretty high, though, depending on the diode. Here's an excerpt from the datasheet for a 1N4001 diode. That's a fairly common diode used in rectifiers. Notice that the peak reverse range is 50 volts. If you get much higher than 50 volts in the reverse direction, the diode is going to break down and allow current to flow backward through the diode. This excerpt from the datasheet shows the reverse current versus voltage. This is actually for the 4000 series. Remember, the 4001 is only good to about 60 volts in reverse mode. But notice for that reverse voltage, at 25 degrees C, which is about room temperature, we're really only talking about 5 times 10 to the minus 8th amps. That's very low. And if we look at the characteristic curves for the forward part of the graph, that is where the diode is conducting in normal mode, you'll see that at about 25 degrees C or room temperature, at 100 milliamps, the drop across the diode is only about 0.8 volts. And all the way up to about an amp, it doesn't get to more than 0.9 volts across the diode. That's pretty consistent over a pretty wide range of currents. Let's take a look at that in the lab. In this example, I've hooked a potentiometer up in series with a diode, and we're measuring the voltage across the diode as we increase the current slowly from about 0.16 amps up to about 0.75 amps. Notice how that although the voltage changes across the diode, it doesn't change by all that much given the huge range of current that we're changing. In fact, if this had been a resistor instead of a diode, that voltage drop would have increased significantly over that range. There's actually a practical application in this type of diode behavior. Here, for example, I needed to drop 2.1 volts consistently over a wide range of current. By putting 3 silicon diodes in series, like shown in the schematic, I can drop 2.1 to 2.4 volts consistently over a wide range of currents. Now you'll notice I said silicon diodes. There are also diodes that are made of germanium, and germanium diodes have different characteristics where the forward voltage drop is approximately 0.3 volts as opposed to 0.7 volts. Here's another practical application for rectifier diodes. In this circuit, called a half-wave rectifier, we're able to take an AC signal and convert it to a DC signal. Remember, current can only pass in one direction through the diode. So when the diode is forward biased, that portion of the signal, in this case the top of the sine waves, is able to pass. But when the sine wave goes negative, the diode becomes reverse biased and the current won't pass through the diode. Notice that the rectified signal, in red, is a little bit lower than the unrectified signal. That's because of the 0.7 volt drop taking place across the diode itself. And here's a half-wave rectifier in the lab. We've got a diode in series with a 10K resistor, and we're inputting a sine wave and measuring the output across the resistor. And here's the result on the oscilloscope. Note that the peak in blue, which is the voltage across the resistor, is slightly less than the peak of the input signal. That's the 0.7 volt, 0.8 volt across the diode. Remember, Ohm's law still holds true. In this example circuit, we see a full wave rectifier. Here, we use a diode configuration called a bridge to rectify both halves of the sine wave. We'll look at one half at a time. So here, the blue arrows show the direction of current for the positive half of the sine wave. Current goes through the first diode, through the load, back up, through a second diode, and then returns to the transformer. The bottom half, or negative portion of the sine wave, goes through that lower diode, through the load, back through that upper diode, and returns to the other side of the transformer. So we're actually dealing with both halves of the sine wave. However, what's really interesting and important is that the current is going through the load in the same direction for both halves of the sine wave. In essence, what we're doing is flipping the lower half of the sine wave and turning it from a negative peak into a positive peak, resulting in the signal that you see here in red. Let's look at a few more practical applications. A rectifier diode can also be used to provide input polarity protection. Here in this circuit, you cannot reverse the positive and negative on the input. Well, you could, but it won't have any effect on the circuit because current will only flow when the positive is connected to the positive input terminal and the negative is connected to the negative input terminal. If you connect power the wrong way around, the diode will block any reverse current and protect your circuit. So here's an example of reverse voltage protection. Got a series resistor and diode, and notice that when I reverse the polarity of the input, the voltage across the resistor goes pretty close to zero. And if I put it back to normal polarity, at least what's intended, the voltage goes to 8.44 across the resistor. And here's an extremely important application for a rectifier type diode. This is called flyback protection. Whenever you have an inductive load, like a motor, or a relay coil with current flowing through it, there's a magnetic field that builds up. That's how an inductor stores energy, in the form of a magnetic field. When you cut that current, open a switch, for example, or in this case, a MOSFET or transistor, that magnetic field begins to collapse. Because of conservation of energy and the physics involved, as that magnetic field collapses, a huge voltage builds up across that coil until it can release that energy in the form of current flow. So if there's no path for the current to flow, that voltage will continue to build, and eventually it'll punch holes in the junction of that transistor and ruin the transistor. In fact, that's called the flyback effect. And that's how flyback transformers in old television sets used to work. They were able to generate 25,000 volts from the 120 volt input. In fact, most boost converters, where you see a 5 volt to 30 volt boost converter, works that same way on the flyback effect. It's extremely important that whenever you have an inductive load, a coil or a motor, that's being controlled by a transistor, you need to put a flyback diode across that coil, or you will burn out your transistor almost every time. Well, I hope you liked that and learned a little something. And if you did, well, how about a like and a share? And if you subscribe, you won't miss any future content. Until next time, cheers.